We've learned that a functional group is an atom or a group of atoms present in a molecule, which determines the characteristic properties of the molecule. For example, methanol, ethanol, and propanol all contain the hydroxyl functional group. All these compounds react with sodium metal and liberate hydrogen. Thus, we can conclude that organic compounds that have similar functional groups show similar chemical reactions. Functional groups play an important role in determining the properties of a compound and are used to organize organic compounds in different classes. Based on the structure of the compounds, they have been organized into classes and assigned IUPAC group prefix and suffix. The alkane group suffix is ane, A-N-E. The alkene group suffix is ene. The alkyne group suffix is ine. The halide group prefix is halo. The alcohol group prefix is hydroxy and the group suffix is -ol. The aldehyde group prefix is formyl or oxo and the group suffix is -al. The ketone group prefix is oxo and the group suffix is -one. The nitrile group prefix is cyano and the suffix is nitrile. The ether group prefix is alkoxy. The carboxylic acid group prefix is carboxy and the suffix is oic acid. The carboxylate ion group suffix is -oate. The ester group prefix is alkoxycarbonyl and the suffix is -oate. The acyl halide group prefix is halocarbonyl and the suffix is oil halide. The amine group prefix is amino and the suffix is amine. The amide group prefix is carbamoyl and the suffix is amide. And the nitro group prefix is nitro. The sulfonic acid's prefix is sulfo and the group suffix is sulfonic acid. Now let's see how we can use the prefix and suffix to assign names to compounds. Step 1. Identify the functional group in the compound. In this example, the functional group OH belongs to the class alcohol. As per the IUPAC system, the suffix for the alcohol group is OL. Step 2. Number the longest chain. If we number the chain from right to left, then the OH group is on second position. And if we number the carbon chain from left to right, then the OH group is on fourth position. As per the naming convention, functional group should be attached to the carbon atom with the lowest possible number. Hence, case 1 is the correct way of numbering. Step 3. Assign a root word. As there are 5 carbon atoms in the chain, the root word will be pent. Step 4. Assign a primary suffix. The chain only contains single bonds. Hence, the primary suffix will be ane. Step 5. Assign a secondary suffix. The functional group is OH, that is alcohol. Hence, the secondary suffix will be ol, OL. Step 6. Specify the position of the functional group. the functional group OH is present at the second position. Hence, the position of the functional group will be 2. Thus, the name of the compound is pentan-2-ol. But some compounds have more than one functional group. These are known as polyfunctional compounds. In such compounds, one of the functional groups is chosen as the principal functional group. The principal functional group is selected based on the order of decreasing priority as shown here. Carboxylic acid has the highest priority, followed by sulfonic acid. Esters, alkyl halides, amides, nitriles, aldehydes, ketones, alcohols, amines, alkenes and alkynes. In the given compound, carboxylic acid will be the principal functional group, as it has higher priority than the ketone functional group. The name of the compound is written on the basis of the principal functional group. For this, we need to start numbering the carbon chain from the end nearer to the carbon atom to which the principal functional group is attached. The principal functional group will come as a suffix. For carboxylic acid, the suffix oic acid is used. The other functional groups act as substituents, and they are written by using appropriate prefixes. Here, the substituent is ketone, and the prefix used for ketone is oxo. Thus, the name of the compound is 5-oxohexanoic acid. If the same functional group appears more than once in a compound, we name the compound by adding di, tri, etc. before the suffix, and the full name of parent alkane is written before the suffix. In this case, since 2 carbons are present, therefore the word root is eth. A single bond is present, therefore the prefix is ane. Hence, the name of the compound is ethane 1,2-diol. Now let's name this compound. In this compound, there are 2 functional groups attached, nitrile group and alcohol group. As the nitrile group has higher priority than alcohol group, we will number the carbon chain such that the carbon of nitrile group gets position 1. Hence, the name of the compound will be 3-hydroxy-4-methyl-pent-4-ene-1-nitrile. The terminal E of the parent chain is retained as it is followed by a consonant and not by a vowel or Y. On the other hand, in the next compound shown here, there is a double bond and a triple bond. In IUPAC nomenclature of organic compounds, a double bond gets preference over a triple bond. Hence, the name of the compound will be pent-3-ine-1-ene. Monosubstituted benzene has only one substituent attached to the benzene ring. While writing the IUPAC name of the monosubstituted benzene, the substituent's name is placed as a prefix to the word benzene. For example, in this compound, the substituent is nitro. Hence, the name of the substituent, which is nitro, is placed as a prefix to the name of the parent compound benzene and the name of the compound becomes nitrobenzene. Similarly, if the substituent is bromine, then the name of the compound is bromobenzene. Now let us name the following monosubstituted benzenes having the substituents methyl, methoxy, amino, and hydroxy respectively. The names of these compounds are methylbenzene, methoxybenzene, aminobenzene, and hydroxybenzene. The common names for these compounds are also widely in use. The common names for these compounds are toluene, anisole, aniline, and phenol respectively. Now let us discuss the nomenclature of the benzene that has more than one substituent. If more than one substituent is present, then the positions of the substituents are indicated by numbering the carbon atoms of the ring. The numbering is done in such a way that the sum of the locants is the least. This means that the substituents should be located at the lowest numbers possible. Let us understand this by considering the following two cases. In case 1, the carbon atoms are numbered in the clockwise direction. As a result, the two bromine atoms are present at the positions 1 and 3. In case 2, the numbering of carbon atom is done in the anti-clockwise direction. As a result, the two bromine atoms are present at the positions 1 and 5. According to the rule, case 1 follows the correct way of numbering. 3 isomers are possible for a disubstituted benzene. These 3 isomers are differentiated in the trivial system by using the names ortho, para, and meta, which are abbreviated as O, P, and M respectively. The positions of the substituents in a disubstituted benzene is thus indicated by using the appropriate prefix ortho, meta, or para. When the substituents are present on the adjacent positions of the benzene ring, that is, on the first and second positions, then in the IUPAC system of nomenclature, the positions of these substituents are indicated as 1, 2, and in trivial system, the prefix ortho is used as shown here. For example, in this compound, the substituent bromine is present at 1 and 2 positions. Hence, the name of the compound is 1,2-dibromobenzene or ortho-dibromobenzene. When the substituents are present at the alternate position of the benzene ring, that is, on the first and third positions, then, in the IUPAC system, the positions of these substituents are indicated as 1, 3, and in the trivial system, the prefix meta is used as shown here. For example, in this compound, the substituent bromine is present at 1 and 3 positions. Hence, the name of the compound is 1,3-dibromobenzene or meta-dibromobenzene. When the substituents are present on diagonally opposite positions of the benzene ring, that is, at 1 and 4 positions, then, in the IUPAC system, the position of these substituents are indicated as 1, 4, and in the trivial system, the prefix para is used as shown here. For example, in this compound, the substituent bromine is present at 1 and 4 positions. Hence, the name of the compound is 1,4-dibromobenzene or para-dibromobenzene. Similarly, the names of the following compounds with 2 different substituents on the benzene ring are 2-ethyl-anisole or ortho-ethyl-anisole and 4-nitroaniline or para-nitroaniline respectively. Now let's look at the nomenclature of tri or higher substituted benzene. Tri-substituted benzene has 3 substituents attached to the benzene ring. Let's look at the rules for naming such compounds. Trivial system of nomenclature cannot be employed as it has more than 2 substituents. This compound has 3 bromine groups attached to the benzene ring. If more than 2 substituents are present, then the positions of the groups are indicated by numbering the carbon atoms according to the lowest locant rule. This means the sequence in which the numbering is done should have the lowest combination of numbers. If the carbon atoms are numbered in the clockwise direction, then the bromine substituent is found at positions 1, 2, and 4. If the carbon atoms are numbered in the anticlockwise direction, then the bromine substituent is found at positions 1, 4, and 6. Hence, according to the lowest locant rule, the correct way of numbering is followed in case 1. Thus, the name of the compound is 1,2,4-tribromobenzene. In this compound, there are 3 different substituents attached to the benzene ring. According to lowest locant rule, the substituent positions in the ring are identified. Hence, the name of the compound is 1,chloro,2,4-dinitrobenzene and not 4-chloro,1,3-dinitrobenzene. In certain cases, the common name of the benzene derivative is taken as the base compound. Thus, anisole is a base compound in the following structure. The numbering of the carbon atom starts from the carbon bearing substituent of the base compound. Thus, the carbon bearing substituent of the base compound, methoxy, is assigned the number 1. Then, the direction of numbering is chosen in such a way that the next substituent gets the next lowest number. In case 1, the numbering is done in the clockwise direction. Thus, the next substituent gets the position 2. Hence, the positions of the substituents present are 1, 2, and 4. In case 2, the numbering is done in the anticlockwise direction, and the substituents get the positions 1, 4, and 6. As per the lowest locant rule, case 1 is the correct way of numbering. Thus, the name of the compound is 2-chloro-4-methylanisole. Note that the names of the substituents are written in alphabetical order. Thus, chloro comes first, followed by methyl. In this compound, the benzene ring is attached to an alkane with a functional group. In such cases, the benzene ring is considered as a substituent. The name of the benzene ring, when it acts as the substituent, is phenyl. The phenyl group is written as C6H5 or abbreviated as PH. The 2 bromine atoms act as the functional groups. The alkane is numbered as per the lowest number rule. In case 1, the carbon atoms are numbered from left to right. As a result, the substituent and the functional group are assigned the positions 1, 2, and 3. In case 2, the carbon atoms are numbered from right to left. As a result, the substituent and the functional group are assigned the positions 3, 4, and 5. According to the lowest locant rule, case 1 follows the correct way of numbering. Bromine is attached to the second and third carbon atoms, hence should be named as 2,3-dibromo. Phenyl is attached to the first carbon atom, hence should be named as 1-phenyl. The alkane has 5 carbon atoms, hence should be named as pentane. Thus, the name of the compound is 2,3-dibromo-1-phenylpentane.
Let's take a compound with the molecular formula C4H10 to understand this concept. If we were to draw the structure of C4H10, we could draw it in the two ways shown here. Both the compounds have same number of atoms. That is, 4 carbon atoms and 10 hydrogen atoms. Thus, their molecular formula is the same. The name of the first compound is N-butane and the second compound is isobutane or 2-methylpropane. Both these compounds have different properties. The phenomenon of existence of two or more compounds with the same molecular formula but with different properties is known as isomerism, and the compounds are called isomers. Thus, N-butane and isobutane are isomers. Isomerism can be of two types: structural isomerism and stereoisomerism. The compounds that have the same molecular formula but different structures are known as structural isomers, and the phenomenon is known as structural isomerism. For example, in N-butane and isobutane, the molecular formula is same but their structures are different. Thus, they are structural isomers. Structural isomerism can be of following types: chain isomerism, position isomerism, functional group isomerism, and metamerism. Let's look at chain isomerism. Compounds that have the same molecular formula but different carbon chain, that is, straight or branched chain, are known as chain isomers, and the phenomena is known as chain isomerism. For example, the following 3 chain isomers are possible with molecular formula C5H12. They are N-pentane, isopentane or 2-methylbutane and neopentane or 2,2-dimethylpropane. Here the carbon skeleton is different in each compound, but the molecular formula is the same. Now, let's look at position isomerism. Compounds that have the same molecular formula, same chain, but which differ in the position of the substituent or functional group are known as position isomers, and the phenomenon is known as position isomerism. For example, the molecular formula C3H8O represents 2 position isomers. In case 1, the functional group OH is attached to the first carbon atom. Hence, the name of the compound is propan-1-ol. In case 2, the functional group OH is attached to the second carbon atom. Hence, the name of the compound is propan-2-ol. In both the compounds, the molecular formula is same, but the position of the functional group differs. Next, let's look at functional group isomerism. Compounds that have same molecular formula but different functional groups are known as functional isomers, and the phenomena is known as functional isomerism. Propanone and propanal represent 2 functional isomers having the same molecular formula, C3H6O. Here the functional group differs. That is, in case 1, ketone is the functional group, and in case 2, aldehyde is the functional group. Some examples of functional isomers are alcohols and ethers, cyanides and isocyanides. Finally, let's look at metamerism. Compounds that have the same molecular formula but different alkyl groups attached to the same functional group are called as metamers, and the phenomena is known as metamerism. This type of isomerism occurs due to the difference in the nature of alkyl group attached to the functional group. Metamers always belong to the same homologous series. Let's consider the molecular formula C4H10O. The following isomers can be drawn, that is, methoxypropane and ethoxyethane. Here the alkyl group attached on either side of the functional group is different. In case 1, methyl and propyl are attached to either side of the functional group, and in case 2, ethyl groups are attached to either side of the functional group. Metamers may also be regarded as positional isomers. Some metamers are ethyl aminoethane and methyl aminopropane, 2-pentanone and 3-pentanone. Now let's look at stereoisomerism. In Greek, stereo means space and meros means parts. The isomers which possess the same structural formula but differ in three-dimensional arrangement of atoms or groups in space within the molecule are known as stereoisomerism, and the phenomenon is called stereoisomerism. Stereoisomerism can be of two types: geometrical isomerism and optical isomerism. You'll learn about these stereoisomer types in higher classes.